In the endless stretches of space where stars shine and galaxies drift, incredible mysteries await. From the wild storms on distant planets to the strange depths of black holes, the universe is full of secrets that defy our understanding. Join us on an exciting journey to uncover the most mind-blowing mysteries in our universe. The Great Red Spot on Jupiter, a massive storm larger than Earth, has baffled scientists since its discovery in the 17th century. One of the most mysterious features of this colossal tempest is its longevity. Despite the dynamic and chaotic nature of Jupiter's atmosphere, the Great Red Spot has persisted for over 300 years. Researchers initially thought such a storm would be short-lived due to turbulent winds surrounding it, yet it has remained a dominant feature on the planet. Scientists now suggest that the spot's impressive size and depth, extending possibly 100 miles into the planet's atmosphere, contribute to its prolonged existence by preventing smaller storms from dissipating its energy. Another enigma surrounding the Great Red Spot is its characteristic crimson hue. While the storm is visually striking, the precise reason for its red coloration remains elusive. Various hypotheses propose that the color could be due to complex chemical reactions involving the trace amounts of sulfur and phosphorus-containing compounds in Jupiter's atmosphere. These compounds might be altered by the sun's ultraviolet radiation, resulting in the ruddy appearance of the storm. Indeed, understanding the spot's coloration could offer insights into the chemical composition and environmental processes of Jupiter's upper atmosphere, a region still cloaked in mystery. Saturn's rings are one of the most captivating features in our solar system, spanning hundreds of thousands of miles yet astonishingly thin, no more than roughly 30 feet thick in some places. The primary factor that helps these rings maintain their structure is the gravitational influence of Saturn's numerous moons, often referred to as shepherd moons. These small moons exert gravitational forces that confine the ring particles, preventing them from dispersing into space. For instance, the moons Pan and Atlas play crucial roles in maintaining the integrity of the A ring and the thin F ring, respectively, by corralling the particles within defined boundaries. Additionally, the ring's stability is enhanced by the orbital resonance between certain moon and ring particle orbits. This phenomenon occurs when particles in the rings and the moons orbit at integer ratios, reinforcing gravitational interactions that help maintain the structure and organization of the rings. The result is a series of intricate and dynamic patterns that are continuously shaped and reshaped over time. Astronomers believe that the rings are composed primarily of water ice, mixed with dust and other chemical compounds, reflecting sunlight and creating their luminous appearance. Despite being an ancient structure, believed to be over 100 million years old, these rings are constantly evolving, offering a vivid lesson in celestial mechanics and the delicate balance maintained by gravitational forces in our solar system. The hexagonal storm on Saturn's North Pole is one of the most intriguing atmospheric phenomena observed in our solar system. Initially discovered by the Voyager spacecraft in the early 1980s, this geometric weather pattern is a vast, persistent cloud pattern in the shape of a hexagon, with each side exceeding the diameter of Earth. Scientists attribute the formation of this hexagon to a combination of atmospheric dynamics and fluid mechanics. Essentially, the hexagon is a standing wave pattern in Saturn's atmosphere, caused by the interaction between jets of air moving at different speeds. These atmospheric jets encircle the pole and are shaped by the planet's rapid rotation, which completes a full turn on its axis in just about 10 Earth hours. Laboratory experiments and computer simulations have further elucidated how such a shape could naturally occur. When fluids at different rotational speeds create shear regions, polygonal patterns can emerge. In Saturn's case, the differential rotation speeds in its atmosphere create a stable wave that takes on a hexagonal form. Moreover, the hexagon's stability and persistence suggest it is deeply embedded in Saturn's atmospheric layers, influenced by deeper rotational currents. Another layer of complexity is added by the shifting colors observed within the hexagon over time, driven by seasonal changes that affect the planet's chemical composition and sunlight exposure. Understanding this hexagonal storm not only provides insight into Saturn's meteorological mechanisms, but also offers broader implications for the study of fluid dynamics and atmospheric sciences. Uranus's peculiar rotation, almost sideways compared to the orbital plane of the solar system, is one of its most mysterious and distinctive features. This extreme axial tilt, about 98 degrees, means that Uranus essentially rolls around the Sun on its side, leading to extreme seasonal variations. Scientists believe this unique orientation was likely caused by one or more colossal collisions during the planet's formative years over 4 billion years ago. A massive impact with a protoplanetary body, possibly as large as Earth, could have knocked Uranus into its sideward tilt, forever altering its rotation. Further supporting this collision theory is Uranus's internal heat distribution and magnetic field, which are both highly irregular compared to other planets. The giant impact hypothesis posits that the force of the collision would not only tilt Uranus, but also disrupt its internal structure, affecting its heat distribution from the core to the surface. This disruption might explain why Uranus radiates relatively little heat compared to its fellow gas giants. Additionally, the planet's magnetic field is tilted approximately 60 degrees from its rotational axis and offset from the planet's center, suggesting that its internal dynamics are quite unusual. This asymmetric magnetic field could also result from the turbulent aftermath of the proposed ancient collision, making Uranus a captivating subject for further astronomical study. Neptune's dark spots, first observed by the Voyager 2 spacecraft in 1989, are enigmatic and dynamic storms that fascinate astronomers. Unlike the Great Red Spot on Jupiter, these storms are temporary, appearing and disappearing over several years. The leading theories behind their formation revolve around the planet's atmospheric dynamics and unique composition. Primarily, these dark spots are thought to be high-pressure systems, akin to anticyclones on Earth, formed much higher in Neptune's atmosphere. They appear as dark spots because they lack the translucent, ammonia-rich clouds that permeate other parts of the planet, revealing deeper layers composed of methane and hydrogen sulfide. The stability and movement of these dark spots are attributed to Neptune's differential rotation and intense wind speeds, which can exceed 1,200 miles per hour. These rapid winds and the planet's internal heat create turbulence in the atmosphere, likely fostering conditions conducive to the formation of dark spots. Furthermore, the extreme cold in Neptune's upper atmosphere, around -373 degrees Fahrenheit, contributes to the peculiar chemistry and cloud dynamics, allowing these storms to manifest with their distinct dark appearance. The temporary nature of the dark spots, in contrast to Jupiter's persistent Great Red Spot, suggests that Neptune's atmospheric conditions are highly volatile and undergo significant changes over relatively short timescales, providing an area ripe for ongoing investigation and discovery in planetary science. The asteroid belt, a vast region populated by rocky remnants, lies between the orbits of Mars and Jupiter. Its formation is closely tied to the early dynamics of our solar system, dating back about 4.5 billion years. The prevailing theory suggests that the asteroid belt is comprised of primordial materials that never coalesced into a planet. In the nascent solar system, planetesimals, the building blocks of planets, collided and merged to form the planets we know today. However, in the region of the asteroid belt, Jupiter's immense gravitational influence disrupted this process. The gas giant's powerful gravity stirred up the region, causing collisions to be too violent for accretion into a larger planetary body, resulting instead in a collection of countless smaller fragments. These remnants hold profound secrets about the early solar system's conditions and composition. By studying the asteroids, scientists can glean insights into the primordial material from which the planets formed, offering a window into the processes of planetary formation and differentiation. Certain asteroids are composed of relatively unaltered material, preserving the original chemical signatures from the solar system's birth. These ancient rocks can reveal information about the distribution of water and organic compounds, shedding light on the origins of water and possibly life on Earth. Furthermore, missions like NASA's OSIRIS-REx to Bennu and Japan's Hayabusa 2 to Ryugu aim to return samples from these bodies, promising to unlock more secrets bound within their ancient surfaces. Venus, often referred to as Earth's twin due to its similar size and composition, presents a stark contrast to our own planet, with its hellish environment of scorching temperatures and crushing atmospheric pressure. The transformation of Venus from a potentially habitable world to its current inhospitable state is attributed to a runaway greenhouse effect. Billions of years ago, Venus may have had liquid water and conditions conducive to life. However, intense volcanic activity released vast quantities of carbon dioxide into the atmosphere. Without a robust mechanism to sequester this carbon, like Earth's carbon cycle involving rock weathering and biological processes, the greenhouse gases accumulated unchecked. The thickening carbon dioxide atmosphere trapped increasing amounts of solar heat, leading to skyrocketing temperatures. As the temperatures rose, any existing oceans started to evaporate, adding water vapor, a potent greenhouse gas, into the atmosphere, further amplifying the heating in a vicious cycle. This runaway greenhouse effect led Venus to reach surface temperatures exceeding 800 degrees Fahrenheit, hot enough to melt lead, and pressures over 90 times that of Earth's at sea level. Additionally, the lack of a significant magnetic field allowed the solar wind to strip away lighter elements from the atmosphere, including hydrogen from any water vapor, making the loss of water irreversible. The dramatic transformation of Venus serves as a cautionary tale about the impact of greenhouse gases on planetary climates. Understanding Venus's past and its climatic evolution provides critical insights into atmospheric dynamics and offers valuable lessons for comprehending Earth's climate system and the potential future impacts of anthropogenic climate change. Olympus Mons on Mars stands as the tallest volcano and one of the most striking features in our solar system, rising around 13 miles above the Martian surface, more than twice the height of Mount Everest. Its immense size can be primarily attributed to Mars's lower gravity, which is about 38% that of Earth. This reduced gravitational force allows Martian volcanoes to grow taller before their structure collapses under their own weight. Additionally, the lack of plate tectonics on Mars plays a crucial role. Unlike Earth, where tectonic plates shift and new volcanic structures form over them, Martian volcanoes remain stationary over their magma sources. This allows them to undergo prolonged eruptions and continuous lava flow, accumulating vast amounts of material in one location over millions of years. Despite its prominence, Olympus Mons holds several mysteries that continue to intrigue scientists. One of these is the volcano's relatively young age in geological terms, with estimates suggesting its last eruption occurred around 25 million years ago, a mere blink in the planet's history. This raises questions about the current state of volcanic activity on Mars and whether the planet could still harbor some geothermal activity beneath its surface. Another enigma is the existence of the caldera complex at its summit, which consists of multiple overlapping collapse craters, indicating a series of eruptive phases. Understanding the exact sequence and scale of these eruptions could provide deeper insights into the planet's geological and volcanic history. Furthermore, the sheer size and structure of Olympus Mons, with its broad shield-like shape and immense lava flows, suggest that the volcano's formation involved not only typical basaltic eruptions, but potentially unique volcanic processes not fully understood. The study of Olympus Mons thus offers a significant opportunity to learn about comparative planetology, volcanic activity on other planets, and the evolutionary trajectories of volcanic features in varying planetary environments. The Kuiper Belt, a vast region beyond Neptune's orbit teeming with icy bodies and dwarf planets like Pluto, is a relic from the early solar system and provides crucial insights into its formation and evolution. These Kuiper Belt objects, KBOs, are thought to be remnants of the primordial solar nebula that never coalesced into full-fledged planets. During the solar system's nascent stages, the outer regions contained a vast disk of gas and dust that gradually clumped together into larger bodies through a process called accretion. However, the region's low density and the presence of massive planets like Neptune disrupted the aggregation process, leaving behind a swarm of smaller icy objects. Over billions of years, gravitational interactions, especially with Neptune, have significantly shaped the Kuiper Belt's structure. For example, many KBOs, including Pluto, are in a special orbital resonance with Neptune. Pluto follows a 2-to-3 resonance, meaning it orbits the Sun twice for every 3 Neptune orbits. This gravitational dance ensures their paths do not intersect, stabilizing their orbits. Such resonant interactions have sculpted the Kuiper Belt into a complex and dynamic region, segregating objects into different populations based on their orbital characteristics. The evolution of KBOs like Pluto involves not just their orbital dynamics, but also their internal and surface changes. Pluto's surface, for instance, exhibits a variety of terrains, suggesting a history of geological activity. The New Horizons mission in 2015 revealed that Pluto has mountains, plains, and even evidence of possible cryovolcanism, volcanoes that erupt with water, ammonia, or methane instead of molten rock. These features indicate that despite their distance from the Sun, the KBOs could experience internal heating driven by radioactive decay or tidal interactions, which might cause these icy worlds to remain geologically active over immense timescales. Understanding how Kuiper Belt objects formed and evolved sheds light on the conditions and processes that occurred in the outer solar system. Studying these distant icy bodies helps scientists piece together the broader narrative of planetary formation and migration, providing a fuller picture of our cosmic neighborhood's intricate history. Mercury, the smallest and innermost planet in our solar system, presents a variety of enigmatic features that continue to intrigue scientists. One of the most puzzling anomalies observed on Mercury's surface is the presence of hollows. These are shallow, irregular depressions with bright reflective halos that differentiate them from typical impact craters. The formation mechanisms behind these hollows remain unclear, but they are hypothesized to result from the sublimation or direct transition from solid to gas of volatile elements. Such volatiles might have been brought to the surface by volcanic activity or outgassing from the planet's interior, resulting in the creation of these mysterious, ever-changing depressions as they evaporate under the sun's intense heat. Another anomaly on Mercury's surface is the existence of unusual, large and unexplainable scarps or cliffs known as lobate scarps. These are believed to be thrust faults, formed as Mercury's core cooled and contracted over billions of years. However, what perplexes scientists is the recent evidence suggesting that some of these tectonic features may still be geologically active. Data from NASA's MESSENGER mission indicated that these scarps might have experienced seismic activity in relatively recent geological timescales, which challenges our understanding of Mercury's thermal evolution and raises questions about the planet's current internal dynamism. Additionally, Mercury's extreme temperature fluctuations, which range from 800 degrees Fahrenheit during the day to minus 290 degrees Fahrenheit at night, contribute to surface anomalies. For instance, the planet's surface is dotted with secondary craters and ejecta patterns that seem more chaotic than those on other solar system bodies. This could be due to the interaction between Mercury's regolith and its tenuous exosphere, influenced by solar radiation and micrometeorite impacts. These anomalies on Mercury's surface not only add layers of mystery to the planet, but also hold keys to deciphering the broader processes of planetary formation and evolution. As scientists continue to study Mercury through missions like Bepi Colombo, our understanding of these surface features will likely expand, offering deeper insights into the dynamic history of the smallest rocky planet in our solar system. Detecting exoplanets, which are planets orbiting stars beyond our solar system, is a challenging endeavor given their vast distances and faint visibility compared to their host stars. However, scientists have developed several ingenious methods to discover and study these distant worlds. One of the most successful techniques is the *** transit method ***, which involves observing the periodic dimming of a star's light caused by an exoplanet passing in front of it. These tiny decreases in brightness, though often less than 1%, can be detected by space telescopes like NASA's Kepler and TESS, Transiting Exoplanet Survey satellite. By analyzing these transit events, astronomers can deduce the exoplanet's size, orbital period, and even some atmospheric properties if the planet's atmosphere filters starlight. Another prevalent method is the *** radial velocity or Doppler technique ***, which measures changes in a star's spectrum of light caused by the gravitational pull of an orbiting planet. As the planet orbits, it induces a small wobble in the star's motion, shifting its light spectrum toward the red end when moving away and toward the blue end when moving closer. High-precision spectrometers can detect these minute shifts, allowing scientists to infer the presence of an exoplanet and estimate its mass and orbit. Ground-based observatories equipped with sensitive instruments like the HARPS, High-Accuracy Radial Velocity Planet Searcher, have been particularly effective in utilizing this method. Another fascinating technique is direct imaging which involves capturing pictures of exoplanets directly by blocking the light of the host star. This method is more suited for young, massive exoplanets located far from their stars, often employing specialized instruments and techniques like coronagraphs or star shades to suppress the starlight. While challenging due to the planet's faintness and proximity to their bright parent stars, advancements in adaptive optics and next-generation telescopes like the James Webb Space Telescope aim to enhance the feasibility of this method. There's also the gravitational microlensing method, which takes advantage of the gravitational field of a star and its planet to bend and magnify the light of a more distant background star. When such an alignment occurs, the resulting light curve can reveal the presence of the planet. This technique is particularly useful for detecting planets that orbit far from their host stars or are not easily detectable by other methods. Each detection technique has its strengths and limitations, often providing complementary information that, when combined, offers a richer understanding of these distant worlds. As technology and observational methods continue to advance, the discovery and study of exoplanets will only become more precise, expanding our knowledge of the universe beyond our solar system. Hot Jupiters are a class of exoplanets that are physically similar to Jupiter in terms of their massive size and gaseous composition, but orbit extremely close to their host stars, often closer than Mercury is to the Sun. These exoplanets can have orbital periods as short as a few days, resulting from their close proximity to their star. This proximity causes them to be intensely heated, with temperatures soaring to several thousand degrees Fahrenheit. The intense radiation from the parent star can cause the atmospheric composition of these planets to differ significantly from cooler gas giants, leading to phenomena such as strong winds, significant atmospheric expansion, and potential mass loss by atmospheric evaporation. The exact mechanisms behind the formation and migration of hot Jupiters are still subjects of ongoing research and debate. One leading hypothesis suggests that these giant planets initially form in the cooler outer regions of their star's protoplanetary disk, much like Jupiter in our own solar system. Over time, gravitational interactions with the disk or other giant planets lead them to migrate inwards. These interactions can be explained by different mechanisms, such as disk-driven migration, where interactions between the planet and the gas of the protoplanetary disk create waves that transfer angular momentum and cause the planet to spiral inward. Another possible explanation involves dynamic interactions with other planets or stellar companions. In such scenarios, gravitational perturbations from these bodies could send a giant planet into an elongated elliptical orbit that gradually circularizes and tightens due to tidal forces, ultimately resulting in a close, stable orbit, the hallmark of a hot Jupiter. The presence of hot Jupiters so close to their stars challenges traditional models of planetary system evolution, offering valuable insights into the dynamism and diversity of planetary systems beyond our own. These extreme worlds also serve as natural laboratories for studying atmospheric physics under intense irradiation, contributing to our broader understanding of exoplanetary atmospheres and the myriad ways planet-star interactions can shape planetary systems. The discovery of potentially habitable exoplanets, worlds that might harbor conditions conducive to life, remains one of the most intriguing and challenging frontiers in modern astronomy. One major mystery revolves around the precise definition of habitability. Traditionally, scientists have focused on the habitable zone or Goldilocks zone around a star where conditions are just right for liquid water to exist on a planet's surface. However, recent discoveries suggest that other factors, such as the planet's atmosphere, geological activity, and magnetic field, play significant roles in sustaining life. For instance, the detection of exoplanets around red dwarf stars, like the 7 Earth-sized planets in the TRAPPIST-1 system, raises questions about the potential for habitability around such stars, given their propensity for stellar flares and varying luminosity. Another mystery is the complex nature of these exoplanets' atmospheres and compositions. While the transit method can reveal a lot about a planet's size and orbit, and the radial velocity method can provide its mass, understanding the atmosphere's composition is far more challenging. Recent advances in spectroscopy have allowed astronomers to analyze the light filtered through an exoplanet's atmosphere during a transit event, revealing the presence of compounds like water vapor, methane, and oxygen. However, interpreting these data is fraught with ambiguity. For example, while the presence of oxygen might suggest biological processes, it could also result from non-biological processes such as photodissociation of water molecules. The discovery of potentially habitable exoplanets also poses the enigma of their true climatic and geophysical states. The detection of exoplanets with Earth-like dimensions does not automatically mean they have Earth-like conditions. For instance, the planet's rotation and tilt, ocean currents, and volcanic activity can drastically affect its climate and potential to support life. Instruments like the James Webb Space Telescope aim to offer more detailed analyses of exoplanetary atmospheres, but for now, many questions remain about these distant worlds' true nature. Finally, the mystery extends to the potential for life itself. What if life on other planets does not conform to the biochemistry we know on Earth? The search for biosignatures, indicators of life, might need to be broader than looking for Earth-like conditions and chemistry. The discovery of extremophiles on Earth, organisms that thrive in conditions previously deemed uninhabitable, has broadened our perspective on where life might exist. Hence, scientists are also considering habitability beyond the traditional scope, including subsurface oceans on moons like Europa and Enceladus, which might be mirrored on exoplanets. Each discovery of a potentially habitable exoplanet brings us closer to answering one of humanity's most profound questions. Are we alone in the universe? Yet each discovery also underscores the complexity and diversity of planetary systems, continually expanding our understanding of what it means for a world to be truly habitable. Super-Earths are a fascinating class of exoplanets that are more massive than Earth, but significantly less massive than the ice giants, Neptune and Uranus. Typically, their masses range from about 1 to 10 Earth masses. Despite the name, super-Earths are not necessarily similar to Earth in terms of composition or habitability. They offer a diverse range of characteristics that can differ significantly from our own planet. One of the primary ways super-Earths differ from Earth is in their size and mass, which have significant implications for their structure and geology. A higher mass generally leads to stronger gravitational forces, which in turn affects the planet's atmosphere. Super-Earths might have denser, thicker atmospheres, potentially dominated by gases like hydrogen and helium, particularly if they formed in the outer regions of their star's protoplanetary disk and migrated inward. These thick atmospheres could lead to higher surface pressures and temperatures, making conditions very different from those on Earth. The interior composition of super-Earths can also vary widely. Some might be rocky worlds with large iron cores, while others could be water-rich, resembling scaled-up versions of Earth's oceans. The presence of large quantities of water could lead to extensive global oceans, possibly hundreds of miles deep, creating what are known as water worlds. In such environments, the oceanic pressure at the bottom would be immense, potentially affecting the geochemical cycles and any potential life forms. Another intriguing aspect of super-Earths is their potential for tectonic activity. Larger planets might retain internal heat for longer periods, supporting vigorous plate tectonics, which could be crucial for maintaining a stable climate and recycling essential minerals and gases. However, the exact nature of tectonic processes on super-Earths remains speculative, given that we currently understand tectonics only in the context of Earth. Furthermore, the climate and weather systems on super-Earths could be radically different. Thick atmospheres and strong greenhouse effects might maintain high surface temperatures, while rapid rotation could lead to intense weather patterns and storm systems. Conversely, some super-Earths may have atmospheres with compositions that allow for more temperate climates, potentially creating habitable conditions. Given their diversity, super-Earths represent a broad class of planets that challenge our understanding of planetary formation and habitability. They might range from hostile, high-pressure worlds with crushing atmospheres to temperate, ocean-covered planets with conditions potentially suitable for life. The study of super-Earths is still in its infancy, but with advancements in telescopes and observational techniques, the mysteries of these intriguing planets will likely continue to unfold, deepening our understanding of the myriad ways planets can form and evolve. When scientists began detailed investigations of exoplanet atmospheres, they encountered a series of astonishing discoveries that extended our understanding of planetary science. One of the most unusual features detected was the presence of elements and compounds not commonly found in such forms within our solar system. For instance, on the exoplanet HD 189733b, researchers discovered traces of silicate particles within the upper atmosphere. These silicates likely form rain made of molten glass, which falls sideways due to the planet's extreme wind velocities of up to several kilometers per second. This intriguing atmospheric phenomenon creates a vision of a celestial object quite foreign to Earth's more placid weather systems. Equally fascinating are the photochemical processes occurring in the atmospheres of gas giants that orbit very close to their host stars, known as hot Jupiters. The intense heat from the nearby stars causes a separation of molecular hydrogen into atomic hydrogen, and ultraviolet light from the star can energize these atoms to create a glowing, escaping cloud of hydrogen gas. This was directly observed in the exoplanet HD 209458b, where astronomers noted a comet-like tail composed of hydrogen trailing behind the exoplanet. It points to dynamic atmospheric escape processes that can significantly alter a planet's complexion over astronomical timescales, reshaping our understanding of atmospheric evolution and planetary life cycles. Rogue planets, also known as interstellar planets or orphan planets, are celestial bodies that wander through the vast expanse of space without the gravitational anchor of a parent star. Unlike planets within a solar system that have stable elliptical orbits around a star, rogue planets drift through the galaxy, moving in trajectories set by their often tumultuous past. These solitary travelers are thought to have been ejected from young planetary systems due to gravitational interactions. which may involve close encounters with other massive planets or passing stars. As developing planetary systems undergo chaotic phases, gravitational forces can impart significant velocities to planets, flinging them into interstellar space. The journey of a rogue planet is in many ways a solitary and cold expedition. Without the warmth of a nearby star, these planets rely solely on residual heat from their formation and potentially internal radioactive decay to maintain any semblance of warmth. Surprisingly, it's hypothesized that some rogue planets could harbor subsurface oceans kept liquid by geothermal energy, despite their frigid outer environs. These planets continue their silent voyage, traversing the Milky Way at speeds often reaching tens of kilometers per second. Their paths are influenced only by the gravitational pull of the galaxy and any stars they might pass close to, occasionally altering their trajectory, but never providing the stable orbit they once knew. Studying exoplanetary weather systems presents a myriad of profound challenges, primarily due to the vast distances between us and these distant worlds. Unlike weather observations on Earth, which can be conducted using a plethora of complex instruments and satellites providing high-resolution data, astronomers must rely on indirect methods, such as spectroscopy when examining exoplanets. Spectroscopic observations require incredibly precise measurements of light emanating from or passing through a planet's atmosphere. This task is particularly daunting because the light from the exoplanet is often faint and easily drowned out by the overwhelmingly bright light of its host star. Distinguishing between the two typically involves complex data processing and advanced telescopes equipped with sophisticated instruments, including space-based observatories like the Hubble and James Webb Space Telescopes. Moreover, the dynamic nature of weather systems adds another layer of complexity to these studies. Weather on exoplanets, especially those with extreme environments such as hot Jupiters, can change rapidly and is driven by factors far more diverse than what we're accustomed to on Earth. These include intense stellar radiation, high-speed winds, and unusual atmospheric compositions. Differential heating on the day side and night side of tidally locked planets, which never rotate to show their night side to the star, can lead to fierce storms and broad-scale atmospheric circulation patterns that are incredibly difficult to model with our current understanding. In addition, the limited observational time available on powerful telescopes and the occasional interference from our own atmospheric conditions further hinder the ability to create accurate, long-term weather models for exoplanets. These considerable challenges make the study of exoplanetary weather a frontier filled with both obstacles and exciting potential discoveries. The formation of exoplanets in binary star systems complicates an already intricate process, presenting scenarios where gravitational forces interplay in fascinating and often chaotic ways. In a binary system, where two stars orbit a common center of mass, the gravitational influence of each star can shape the protoplanetary disk, a rotating disk of gas and dust from which planets coalesce, in unique ways. Generally, two primary scenarios dictate how planets might form in these environments: the circumbinary and circumstellar configurations. In a circumbinary setup, planets form in a disk that encircles both stars. Here, the combined gravitational pull of the binary stars influences the protoplanetary material, potentially stabilizing or destabilizing certain regions of the disk. However, the inner parts of the circumbinary disk are usually void of solid material due to dynamic perturbations, pushing the planet formation regions further out. Despite these challenges, discoveries of planets like Kepler-16b, a circumbinary planet, prove that planet formation can and does occur in such conditions, albeit with unique orbital characteristics influenced by the dual star dynamics. Conversely, in a circumstellar scenario, planets form around just one of the stars in the binary pair. The gravitational forces from the companion star can induce eccentricities in the protoplanetary disk, leading to variations in the disk's density and temperature. These variations can either hinder or foster planet formation, depending on how pronounced these gravitational perturbations are. Important factors include the distance between the two stars and the mass ratio of the binary system. Planets in these configurations often have more eccentric orbits compared to those in single-star systems due to ongoing perturbations by the secondary star. This distinctive environment prompts planets to follow unique developmental pathways, showcasing the diverse possibilities of planetary formation in our universe. When scientists search for potential signs of life on exoplanets, they focus on a broad spectrum of biosignatures, indicators that could imply the presence of biological activity. One of the primary biosignatures is the detection of certain gases in a planet's atmosphere, particularly those that are often associated with life as we know it. Oxygen, for instance, is a key indicator because it is continually replenished by biological processes such as photosynthesis on Earth. In the absence of ongoing biological activity, free oxygen would typically react with other elements and not remain in a planet's atmosphere in significant amounts. Similarly, methane is another compelling biosignature, especially when found alongside oxygen, as it would likely need a constant source to maintain equilibrium given its relatively short lifespan in atmospheric conditions. Beyond individual gases, scientists look at the overall atmospheric composition and the potential for complex interactions that could suggest life. For example, the simultaneous presence of gases like ozone and nitrous oxide, or a specific ratio of carbon dioxide and water vapor, might suggest biological processes. In addition to gaseous components, the detection of organic molecules, complex carbon-based compounds that are fundamental to life, can also be a significant indicator. Instruments like those on the James Webb Space Telescope are designed to identify such molecules through detailed spectroscopic analyses of starlight filtered through an exoplanet's atmosphere. Moreover, scientists also observe planetary surface conditions and potential habitability factors. Signs of liquid water, either on or beneath the surface, are considered quintessential markers of life-supporting conditions, as water is a solvent for many biochemical reactions. The planet's position within the habitable zone of its star, where temperatures are conducive to the presence of liquid water, also plays a crucial role. The search for life involves a holistic approach that combines these potential biosignatures, the atmospheric and surface conditions, and understanding the planet's environmental stability over time, giving scientists the tools to make educated guesses about the likelihood of life beyond Earth. Exoplanetary moons, often referred to as exomoons, could significantly contribute to the habitability of the host exoplanets, or even be potential sites of habitability themselves. These moons can play several roles in creating and maintaining environments where life might flourish. One of the primary mechanisms is through tidal heating, which can provide a substantial and consistent source of internal heat, particularly for moons orbiting large gas giants. Tidal heating occurs due to the gravitational pull between the moon and its planet, causing flexing and frictional heating within the moon's interior. This process can maintain subsurface oceans in a liquid state, as is theorized for moons like Europa and Enceladus in our own solar system, thereby offering potential niches for life. Additionally, an exomoon's orbit can influence the axial tilt of its host planet, which in turn can stabilize the planet's climatic conditions. A stable axial tilt ensures more regular seasonal variations, which could foster an environment conducive to complex life by preventing extreme climatic swings. Moons can also aid in bolstering the protection of the host planet's atmosphere from solar wind stripping, particularly if the moon itself possesses a magnetic field. This magnetic shield can create a more stable atmosphere, essential for sustaining liquid water and, consequently, life. Furthermore, exomoons might themselves harbor conditions favorable to life, independent of their host planets. If such moons exist within the habitable zone of their star system, they could potentially have atmospheres, liquid water, and other life-supporting characteristics. Observations with current and upcoming astronomical instruments aim to measure and analyze the atmospheres and compositions of these moons, searching for signs of geological activity, water vapor, and even biosignatures, similar to those sought after on exoplanets. The presence of exomoons adds additional layers of complexity and opportunity to the search for habitable environments beyond our solar system. Their contributions to tidal heating, climatic stability, and atmospheric protection all enhance the potential for life-supporting conditions on both the exomoons and their host exoplanets, making them exciting targets for future exploration and study. Black holes, some of the most enigmatic objects in the universe, come in various types, differing primarily in size and mass. These cosmic entities can be broadly classified into three main categories: stellar mass black holes, supermassive black holes, and intermediate mass black holes, each with distinct formation processes and characteristics. Stellar mass black holes are the most common type and form from the remnants of massive stars. When a star with a mass greater than approximately 25 times that of our Sun exhausts its nuclear fuel, it undergoes a supernova explosion. The core that remains can collapse under its own gravity to a point of infinite density, known as a singularity, enveloped by an event horizon beyond which nothing can escape. These black holes typically range from a few to several tens of solar masses and are scattered throughout galaxies, including our Milky Way. Supermassive black holes residing at the centers of most galaxies are a different beast altogether, boasting masses ranging from hundreds of thousands to billions of solar masses. Their formation is a subject of ongoing research and debate, but several theories exist. One hypothesis suggests they form from the merging of many smaller black holes and massive stars in the dense central regions of young galaxies. Another theory posits that they could have originated from the direct collapse of massive gas clouds in the early universe. Over time, these enigmatic giants grow by accreting matter from their surroundings and merging with other black holes, thus becoming the colossal structures that anchor galaxies. Intermediate mass black holes, occupying the size range between stellar mass and supermassive black holes, remain somewhat elusive and less well understood. These black holes are thought to form through the merging of stellar mass black holes in dense star clusters, or via the direct collapse of very massive stars in low metallicity environments. They range from hundreds to thousands of solar masses and might represent an evolutionary bridge between stellar mass and supermassive black holes. Although few confirmed examples of intermediate mass black holes exist, they offer critical clues about the scaling and growth processes that lead to supermassive black holes. Each type of black hole provides a unique window into the universe's fundamental processes, offering insights into stellar evolution, galaxy formation, and the mysterious nature of gravity itself. Their formation mechanisms, albeit varied and complex, underscore the dynamic and ever-changing cosmos that continues to captivate scientists and enthusiasts alike. Black holes warp space-time through the profound effects of their immense gravitational fields, a concept that stems from Albert Einstein's general theory of relativity. This theory, formulated in the early 20th century, revolutionized our understanding of gravity, revealing that massive objects cause a curvature in the fabric of space-time itself. A black hole, with its intense gravitational pull, represents one of the most extreme examples of this phenomenon. Imagine space-time as a two-dimensional rubber sheet. When you place a massive object like a star on this sheet, it creates a depression or a dip, bending the sheet around it. A black hole, however, acts like placing an enormously heavy and compact object on the sheet, creating a well so deep and steep that it forms a kind of funnel. The closer you get to the black hole, the steeper the curvature becomes, culminating in a singularity at its center, where the curvature of space-time becomes infinite. This warping has several observable effects. For one, light traveling near the black hole takes a curved path due to the highly curved space-time. This phenomenon, known as gravitational lensing, can bend, distort, or even multiply the images of background stars or galaxies, creating spectacular astronomical observations. In the vicinity of the event horizon, the boundary beyond which nothing can escape the black hole's pull, time itself appears to slow down when observed from a distance, a consequence of the intense gravitational field. This effect, predicted by Einstein, is known as time dilation and has been confirmed through various experiments and observations. Moreover, the escape velocity within the event horizon exceeds the speed of light, rendering regular matter and signals unable to escape once they cross this threshold. Additionally, black holes can dramatically influence their surroundings through the accretion of matter. As matter spirals into a black hole, it forms an accretion disk, heating up to extreme temperatures and emitting X-rays and other forms of radiation. This process further underscores the black hole's ability to warp space-time and energy around it. The warping of space-time by black holes offers profound insights into the nature of gravity and the underlying structure of the universe. These intriguing objects continue to be the focus of intense scientific study, pushing the boundaries of our understanding and unveiling new mysteries of the cosmos. The event horizon of a black hole stands as one of the most enigmatic boundaries in the universe, enveloped in various mysteries that challenge our understanding of physics. As the defining edge of a black hole, the event horizon is the point beyond which nothing, not even light, can escape the gravitational pull of the singularity at the center. This boundary marks a region where our conventional understanding of space and time begins to break down. One of the most profound mysteries surrounding the event horizon is what happens to the information about matter that falls into a black hole. This conundrum, known as the information paradox, arises from the apparent contradiction between general relativity and quantum mechanics. According to general relativity, any information about the matter that crosses the event horizon is ultimately lost to the singularity, where it is thought to be compressed into an infinitely small point. However, quantum mechanics, which governs the microcosmic world, dictates that information must be conserved. The clash between these two foundational principles of physics has led to various theories and debates, most notably involving Stephen Hawking's proposal of Hawking radiation. Hawking suggested that black holes could emit radiation due to quantum effects near the event horizon, gradually evaporating over time and potentially allowing information to be released back into the universe in some scrambled form. This idea has spurred countless discussions and remains an active area of research. Another significant mystery revolves around the exact nature of the singularity that lies within the event horizon. The singularity is a point where gravitational forces become infinite and space-time curvature reaches an extreme. Our current laws of physics, particularly general relativity, cannot adequately describe conditions at the singularity. This has led scientists to explore theories of quantum gravity, such as string theory and loop quantum gravity, in the hope of developing a unified framework that can reconcile the discrepancies between quantum mechanics and general relativity. These efforts aim to unveil the true nature of black holes' cores and the ultimate fate of the matter and energy trapped within. The event horizon also raises questions about the observable effects experienced by an object approaching it. From the perspective of a distant observer, an object falling into a black hole appears to slow down and become increasingly redshifted as it approaches the event horizon due to extreme gravitational time dilation. However, from the viewpoint of the object itself, it would cross the event horizon without experiencing any dramatic changes, heading towards the singularity. This paradox of perspectives underscores the complex and counterintuitive nature of relativity in the realm of intense gravitational fields. The event horizon of a black hole serves as a frontier where our understanding of the universe is put to the test, posing deep and tantalizing mysteries about the fundamental nature of matter, energy, space, and time. These unresolved questions continue to inspire theoretical and observational endeavors, driving the quest for new physics that can illuminate the darkest corners of our cosmos. Inside a black hole, current theories suggest a realm of extremes where our conventional understanding of physics bends and possibly breaks. The journey toward comprehending what happens within a black hole begins at the event horizon, the boundary beyond which nothing can escape. Once an object crosses this threshold, it is inescapably drawn toward the core of the black hole, experiencing conditions unlike any in the observable universe. As one falls into a black hole, the experience would drastically differ depending on the black hole's size. For a stellar mass black hole, the gravitational forces at the event horizon are immensely strong, causing a phenomenon known as spaghettification. This results from a steep gradient in gravitational pull between the head and feet of an object, or person, stretching it into a long, thin shape as it approaches the singularity. In contrast, for a supermassive black hole, being several million to billion times the mass of the Sun, the tidal forces at the event horizon are less severe, allowing one to cross the boundary without immediate spaghettification, but this relative calm is short-lived as one moves deeper toward the center. The core of a black hole contains a singularity, a point where densities soar to infinity and the curvature of space-time becomes infinite. According to general relativity, all matter and information entering a black hole inevitably collapse into this infinitely small point where gravitational forces are immeasurable. However, this depiction confronts the limits of general relativity, prompting numerous theoretical physicists to seek a unifying theory that incorporates quantum mechanics, often referred to as quantum gravity. Competing theories like string theory or loop quantum gravity endeavor to describe the singularity in terms of quantum mechanics, potentially replacing the singularity with a more comprehensible structural core. Beyond these internal dynamics, another perplexing question is the fate of information that crosses the event horizon. This leads to the so-called information paradox. Quantum mechanics posits that information is never truly lost, while the classical view of black holes suggests it is irretrievably destroyed within the singularity. To reconcile these differences, Stephen Hawking proposed that black holes emit radiation, now known as Hawking radiation, through quantum effects near the event horizon. This radiation could result in the gradual evaporation of black holes over cosmic timescales, suggesting that the information could be diffused back into the universe, albeit in an exceedingly altered state. This hypothesis is still a topic of vigorous debate and study, seeking to unify these apparent contradictions between the realms of quantum mechanics and general relativity. While our understanding of what transpires within a black hole remains incomplete and highly theoretical, current models portray it as a stage for extraordinary gravitational phenomena and extraordinary quantum effects. As research advances, we may edge closer to unraveling these mysteries, potentially discovering new realms of physics that transcend our current scientific boundaries. Black holes consume matter and energy from their surroundings through the process of accretion, a gravitationally driven mechanism that can transform seemingly empty space into regions of intense activity and light. The accretion process plays a crucial role in the growth and evolution of black holes, allowing them to gather mass from nearby stars, gas, and even light. When matter such as gas, dust, or stars ventures too close to a black hole, it becomes trapped by the black hole's extreme gravitational pull. Instead of plunging directly into the black hole, this material often forms an accretion disk, a swirling disk of matter spiraling inward. The matter in the disk experiences friction and compression, heating up to extremely high temperatures, sometimes reaching millions of degrees. This superheated material emits various forms of radiation, particularly in the X-ray spectrum, allowing astronomers to detect and study black holes, even though the black holes themselves emit no light. The intense gravitational gradient near the black hole ensures that the infalling matter loses angular momentum and energy, progressively spiraling closer to the event horizon. As the matter approaches the event horizon, relativistic effects become significant. The emitted radiation from this region is subject to gravitational redshift, whereby light is stretched to longer wavelengths, a phenomenon predicted by Einstein's theory of general relativity. This redshift serves as a powerful observational tool, providing clues about the behavior of matter in extreme gravitational fields. In addition to consuming matter from its immediate vicinity, black holes in binary systems can siphon material directly from a companion star. This happens when the star fills its Roche lobe, allowing matter to flow through the inner Lagrange point toward the black hole, forming an accretion stream. This stream feeds the accretion disk, leading to intensified radiation and energetic outbursts detectable across vast distances. The process is not entirely efficient, and some fraction of the accretion material is expelled from the black hole's vicinity in the form of powerful jets and winds. These jets, often observed in supermassive black holes at the centers of galaxies, can shoot out material at velocities approaching the speed of light, extending across thousands or even millions of light years. This phenomenon, known as relativistic jet emission, demonstrates the extraordinary power of black holes and their capacity to influence their cosmic environments. The resulting feedback, where the jets interact with the galaxy and intergalactic medium, can play a significant role in regulating galaxy formation and evolution. Black holes consume matter and energy through gravitationally driven accretion processes, forming highly energetic disks and jets. These mechanisms allow them to grow and exert significant influence over their surroundings, transforming in particular through the emission of high-energy radiation and powerful relativistic jets. Despite their profound gravitational pull, these processes let black holes escape their otherwise invisible nature, offering windows into the extreme physical conditions near their event horizons. Supermassive black holes residing at the centers of most galaxies, including our own Milky Way, are among the universe's most intriguing and enigmatic objects. Despite significant advances in astronomy and astrophysics, many mysteries still surround these colossal entities, from their origins to their roles in galactic evolution. One of the most profound mysteries is how supermassive black holes form and grow to their immense sizes, ranging from millions to billions of times the mass of our Sun. Two leading theories aim to explain their origins. One posits that supermassive black holes formed from the direct collapse of massive gas clouds in the early universe, bypassing the intermediate stages of star formation. The other theory suggests they grew from smaller seed black holes, which could have originated from massive stars or earlier generation star clusters, accumulating mass through the accretion of gas, dust, and mergers with other black holes. However, neither theory fully accounts for the presence of supermassive black holes in the very early universe, observed to exist just a few 100 million years after the Big Bang. The relationship between supermassive black holes and their host galaxies presents another profound puzzle. Observations have revealed a tight correlation between the mass of a supermassive black hole and the properties of the galactic bulge, such as the velocity dispersion of stars. This empirical relationship, known as the M-sigma relation, suggests that black holes and their host galaxies co-evolve. Yet the mechanisms driving this coevolution remain unclear. Supermassive black holes significantly affect their environments, primarily through energetic feedback processes involving jets and radiation emitted from accretion disks. These processes can suppress or trigger star formation, regulate gas distribution, and sculpt galactic structures. Understanding these feedback mechanisms in detail is essential to developing a cohesive picture of galaxy formation and evolution. Additionally, the nature of the accretion processes near supermassive black holes continues to challenge our understanding. The physics governing the behavior of matter in the extreme gravitational and electromagnetic environments near black holes, including how some matter forms relativistic jets, remains a topic of active theoretical and observational research. Instruments like the Event Horizon Telescope, which provided the first direct image of a black hole's event horizon in 2019, are crucial for probing these extreme conditions and shedding light on the complex dynamics at play. Supermassive black holes also raise questions about the ultimate fate of galaxies. As galaxies merge, their central black holes are expected to form binaries and eventually coalesce into a single, more massive black hole. The detection of gravitational waves from such mergers, as observed by LIGO and Virgo, is beginning to provide insights into these cosmic events. However, direct observation and detailed understanding of the intermediate stages of black hole mergers offer a fertile ground for future discoveries. While we have made tremendous strides in observing and understanding supermassive black holes, many mysteries remain. From their formation and growth to their intricate relationship with their host galaxies and the dynamics of accretion and feedback processes, supermassive black holes continue to pose some of the most captivating questions in modern astrophysics. Ongoing and future observations, combined with sophisticated theoretical models, promise to deepen our understanding of these colossal enigmas and their role in shaping the universe. Black holes, by their very nature, emit no light and thus cannot be observed directly. However, scientists have developed ingenious methods to study these enigmatic objects indirectly, relying on their interactions with surrounding matter and the gravitational effects they exert on nearby objects. One of the most effective ways to observe black holes is by studying the X-ray emissions from their accretion disks. When matter from a companion star, interstellar gas, or other sources gets drawn toward a black hole, it forms a swirling accretion disk. As this matter spirals inward, it heats up due to friction and compression, reaching temperatures of millions of degrees. This hot material emits X-rays before crossing the event horizon. Space-based telescopes like NASA's Chandra X-ray Observatory, ESA's XMM Newton, and now the James Webb Space Telescope provide detailed observations of these high-energy emissions, revealing the presence and properties of black holes. Another crucial method involves observing the gravitational influence of black holes on nearby stars and gas clouds. For instance, astronomers can track the orbits of stars near the center of our galaxy, where the supermassive black hole Sagittarius A* resides. By meticulously measuring these stellar orbits, scientists can infer the mass and the location of the black hole that is exerting the necessary gravitational force to govern such orbits. This technique was instrumental in providing compelling evidence for the existence of Sagittarius A*, earning the 2020 Nobel Prize in Physics for Reinhard Genzel and Andrea Ghez. Additionally, gravitational lensing provides another indirect method to study black holes. When a black hole passes between a distant light source, like a star or galaxy, and an observer on Earth, its immense gravitational field warps the space-time around it, bending and magnifying the light from the background object. This lensing effect can create multiple images or distortions of the light source, which scientists can analyze to gather information about the black hole's mass and properties. More recently, the detection of gravitational waves has opened a new avenue for studying black holes. Predicted by Einstein's general theory of relativity and first detected by the LIGO and Virgo observatories in 2015, gravitational waves are ripples in space-time generated by the acceleration of massive objects, such as the merging of black holes. The wave patterns recorded by these observatories provide insights into the masses and spins of merging black holes, giving us a direct look at black hole interactions. Furthermore, the Event Horizon Telescope, EHT, represents a groundbreaking development in imaging the event horizon, the boundary beyond which nothing can escape a black hole's gravitational pull. In 2019, the EHT collaboration released the first ever image of a black hole's shadow in the galaxy M87. This achievement relied on a global network of radio telescopes working in unison to simulate a planet-sized observatory, capable of resolving the fine details in the vicinity of a black hole. By analyzing the light bending and radiation near the event horizon, scientists can test predictions of general relativity and gain deeper insights into the nature of black holes. While direct observation of black holes is impossible due to their light-absorbing nature, scientists have developed a multitude of indirect methods to study them. By examining X-ray emissions, stellar dynamics, gravitational lensing effects, gravitational wave signals, and direct imaging of event horizons, researchers can unveil the properties and behaviors of these elusive cosmic giants, enriching our understanding of the universe. Hawking radiation, proposed by the eminent physicist Stephen Hawking in 1974, is a theoretical prediction that bridges the realms of quantum mechanics and general relativity, suggesting that black holes are not entirely black, but emit radiation. This groundbreaking concept has profound implications for our understanding of black holes and the fundamental principles of physics. Hawking radiation arises from the peculiarities of quantum field theory in the context of curved space-time around a black hole. According to quantum mechanics, even in the vacuum of space, particle-antiparticle pairs continuously pop into and out of existence. Near the event horizon of a black hole, the intense gravitational field can separate these pairs. In some cases, one particle falls into the black hole while its counterpart escapes into space. The escaping particle appears as radiation emitted from the black hole. To an external observer, this phenomenon results in the gradual reduction of the black hole's mass and energy over time, a process that theoretically could lead to the black hole's eventual evaporation. The significance of Hawking radiation in black hole research is multifaceted. Firstly, it introduces the idea that black holes have a finite lifetime, challenging the notion of black holes as eternal, unchanging objects. The evaporation process is slow for massive black holes and rapid for smaller ones, suggesting that primordial black holes, formed shortly after the Big Bang, might have already evaporated completely or be in the final stages of their decay, potentially leaving observable effects that astronomers could detect. This theoretical radiation also touches on the heart of one of the most profound puzzles in modern physics, the information paradox. According to classical mechanics, any information about the matter that falls into a black hole is lost forever within the singularity. However, quantum mechanics insists that information cannot be destroyed. Hawking radiation suggests that, over immense timescales, information might be encoded in the radiation emitted from the black hole, thereby reconciling this apparent contradiction. While the exact mechanism for how information is preserved remains unclear, the hypothesis has spurred significant discussions and research efforts aimed at understanding the nature of information conservation in the universe. Moreover, Hawking radiation bridges the gap between quantum mechanics and general relativity, two pillars of modern physics that typically operate in very different regimes. By demonstrating that quantum effects can have macroscopic consequences in the strong gravitational fields of a black hole, Hawking's theory provides key insights into the quest for a unified theory of quantum gravity. Such a theory would encapsulate all fundamental forces in one framework, representing the ultimate goal of theoretical physics. Hawking radiation is not just a theoretical curiosity, but a significant cornerstone in our understanding of black holes. It reshapes our perception of these cosmic entities, hints at deeper principles governing the universe, and energizes the quest to reconcile the inconsistencies between quantum mechanics and general relativity, opening doors to new realms of discovery in the physics of the cosmos. Black holes, often viewed as the dark consumers of the cosmos, harbor potential for revolutionary applications in space travel and energy generation, albeit these ideas still hover within the domain of speculative science. Harnessing black holes, given their extreme gravitational and energetic properties, could radically transform our technological capabilities. One intriguing concept for space travel involves using rotating, or Kerr, black holes as cosmic shortcuts through space-time. According to solutions of Einstein's field equations, a rotating black hole might possess a region known as the ergosphere, where space-time is dragged around at high speeds. Some theories, most notably involving hypothetical constructs like wormholes, propose that Kerr black holes could form gateways between distant points in space and time. If traversable wormholes exist, they could potentially allow spacecraft to travel vast cosmic distances instantaneously by entering one end of the wormhole and emerging at another location in the universe. Such a mechanism, while currently beyond our technological reach and perhaps speculative, stimulates imagination about future possibilities. Developing technology capable of navigating and surviving the intense gravitational and tidal forces near a black hole remains a formidable challenge. Energy extraction from black holes, on the other hand, appears to be a more grounded possibility, leveraging phenomena like the Penrose process and Hawking radiation. The Penrose process, theorized by physicist Roger Penrose, suggests a method to extract energy from the ergosphere of a rotating black hole. In this process, an object or particle entering the ergosphere could split into two, with one part being consumed by the black hole while the other escapes. The escaping part could gain energy extracted from the black hole's rotational energy. This harvested energy, in theory, could be used for various applications, potentially offering an incredibly potent power source. Moreover, theoretical research into Hawking radiation posits another method of energy generation. As black holes slowly evaporate via Hawking radiation, they emit particles that carry away energy. Capturing this radiation could, hypothetically, provide a steady stream of energy. A more extreme idea involves creating microscopic black holes, which would evaporate much faster, providing intense bursts of energy. Some proposed scenarios involve particle accelerators or other advanced technologies to intentionally create and harness such micro black holes for energy production. However, these notions face significant technological and safety hurdles before becoming feasible. In addition, black holes could theoretically power interstellar propulsion systems. One speculative idea involves the use of a black hole as a power source for a black hole bomb propulsion system. This involves placing a black hole within a massive reflecting shell that could amplify energy extracted from the black hole's rotational energy, creating a powerful thrust for propulsion. Science fiction has also explored concepts like the black hole starship, using controlled black holes as energy sources to propel spacecraft at relativistic speeds. While these ideas currently lie in the realm of theoretical speculation, ongoing advancements in our understanding of quantum mechanics, general relativity, and particle physics might bring some of these concepts closer to reality. Harnessing the power of black holes could revolutionize our energy systems and propel humanity toward an era of interstellar exploration, showcasing the potential of these mysterious cosmic objects to unlock extraordinary new capabilities in energy and space travel. Recent discoveries about black hole mergers have dramatically expanded our understanding of the universe in ways we couldn't have predicted. One of the most captivating findings emerged when the LIGO and Virgo observatories detected gravitational waves, those subtle ripples in the fabric of space-time brought about by the collision of black holes. These events, which often involve black holes several times the mass of our Sun, unleash an unfathomable amount of energy, equivalent to several solar masses being converted directly into gravitational waves. The precision of these detections allows scientists to confirm the existence of intermediate mass black holes, which fill in the long-standing gap between small stellar mass black holes and the supermassive ones found at the centers of galaxies. Equally exciting are the broader implications for our understanding of the cosmos. Black hole mergers serve as natural laboratories for testing Einstein's theory of general relativity under extreme conditions. Recent findings hint at the possibility that these mergers might not always produce a perfect ring-down or settling of the newly formed black hole, suggesting there might be more exotic physics at play. Additionally, these events are key to solving the mystery of heavy element formation. The intense gravitational interactions and resulting high-energy phenomena have been proposed as sites where elements heavier than iron could be forged, something stellar nucleosynthesis alone struggles to fully explain. The continuous observation and analysis of such cosmic phenomena could potentially unlock answers to some of the universe's most profound mysteries, reshaping our understanding of its very fabric.